Welcome back to OwlsPrep. Topic 1.4, Polynomial Functions and Rates of Change. The objective for this topic is one sentence. Identify key characteristics of polynomial functions related to rates of change. So that's exactly what we'll go through. What a polynomial is and the three names attached to it. Where the graph turns, which of those turns is the biggest, what two zeros force to happen in between, what an even degree guarantees, and where the curve changes the way it bends. Start with what a polynomial actually is. A non-constant polynomial function of x is anything you can write in this form. A sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so on, down to a 1x plus a 0. Here n is a positive integer. Every coefficient is a real number, and the leading coefficient of sub n is not 0. Three names come out of that. The degree is n, the highest power. The leading term is a sub nx to the n, the term carrying that highest power. And the leading coefficient is a sub n, the number sitting in front of it. So for p of x equals 2x to the fourth minus 5x cubed plus x minus 7, the degree is 4, the leading term is 2x to the fourth, and the leading coefficient is 2. One edge case worth remembering. A non-zero constant is also a polynomial of degree 0. To find those characteristics, we work with the rate of change. So let's set one example up. Take f of x equals x cubed minus 3x and read its output at equally spaced inputs. -2, then 2, then 0, then -2, then 2. Over each step, the average rate of change in output over change in input, is the slope of the line joining that pair of points. Those come out as +4, -2, -2, and +4. Now the sign is what carries the meaning. A positive rate means the function is increasing, a negative rate means it's decreasing. Plus, minus, minus, plus. So the graph goes up, then down across the middle, then up again. Here's the first key characteristic. Wherever a polynomial function switches between increasing and decreasing, it has a local, or relative, maximum or minimum. Our rates go from +4 to -2 at x equals -1. Increasing turning into decreasing, so that's a local maximum at the point -1, 2. Then from -2 to +4 at x equals 1. Decreasing turning into increasing, a local minimum at 1, -2. And keep the word local honest. It only means highest or lowest compared to the points near it. It says nothing yet about the function overall. Two things extend that idea. First, endpoints. If the polynomial's domain is restricted and the endpoint is included, that endpoint is a local maximum or minimum as well. On the left is our cubic with its domain cut down to -2 through 0. The turn at -1 is still a local maximum, and now each endpoint counts 2. X equals -2 and x equals 0 are both local minima. Second, global. A local maximum that is greater than all other output values of the function is called the global or absolute maximum, and a local minimum below all the others is the global minimum. Be careful here. Not every polynomial has one. Our cubic doesn't. Its outputs climb without bound one way and fall without bound the other, so it has local extremes, but no global ones. On the right, though, take g of x equals -x squared. Every output is 0 or below, and the vertex reaches 0, so that local maximum really is greater than all the others, a genuine global maximum. The next characteristic lets you conclude something without computing anything. Between every two distinct real zeros of a non-constant polynomial function, there must be at least one input value giving a local maximum or a local minimum. Look at our cubic. It has 3 real zeros. Between the first two, the graph leaves the axis and has to come back to it. And the only way to do that is to turn around, which it does at the local maximum. Between the second and third zeros, the same argument gives the local minimum. So two distinct zeros guarantee at least one turn in between every time. Degree tells you something on its own. A polynomial function of even degree always has either a global maximum or a global minimum. The clearest case is a quadratic. Opening upward, it has a global minimum. Opening downward, it has a global maximum. And either way, that global extreme sits exactly at the vertex. Compare that with our cubic, which has odd degree. It does have a local maximum and a local minimum, but there's no highest or lowest output overall. The graph keeps climbing on one side and keeps dropping on the other. So an even degree guarantees you one global extreme. An odd degree doesn't. The last characteristic looks at the rates one more time, but now at the rates themselves, not their sign. On the left side, they are decreasing, 4 down to -2. Where the rate of change is decreasing, the graph is concave down. On the right, they turn around and increase, back up to 4, and there the graph is concave up. A point of inflection is exactly that switch, an input value where the rate of change of the function changes from decreasing to increasing, or from increasing to decreasing. Equivalently, it's where the graph changes from concave down to concave up, or from concave up to concave down. For our cubic, that happens at x equals 0. So those are the key characteristics of a polynomial function tied to its rate of change. 1. The degree, leading term, and leading coefficient, which you read straight off the polynomial. 2. Wherever it switches between increasing and decreasing, you get a local maximum or minimum. 3. An included endpoint of a restricted domain counts as 1, 2, and any local extreme that beats every other output is the global one. 4. Between two distinct real zeros, there is always at least one local max or min. 5. An even degree guarantees a global maximum or a global minimum, and for a quadratic, it's at the vertex. And 6. Where the rate of change itself turns around, you have a point of inflection and the concavity flips. Next up, topic 1.5 looks at polynomial functions and complex zeros. See you there.